This conference will now be recorded.
Hi, good morning. Hope you're able to. Good morning. Hope you are able to see my screen.
Yes, sir. Good morning.
Okay, good. So welcome back, and let's continue from where we have left yesterday. So we are on the final step of our project building, of our regression model building. So we have come a long way. Now in the final step, we are figuring out a process to build models using multiple algorithms and with multiple practical hyperparameter tunings, and use techniques such as cross validation to build a lot of models so that we can evaluate them with our test data, which we have separated already, and based on what each of these models, best performing model from every algorithm, we want to compare those metrics, and we want to finalize the winner model and send it to our customer. Once we do that, this project will be done. Okay, so yesterday we generally talked about some basic concepts that are involved at the time of model training. So we talked about train, test, split, and that is a very easy step to accomplish. Yesterday we did it already on our analytical base table. And then we have to now take up another action that is actually adjusting the scaling of all of our features in an appropriate way, and again use a concept called pipeline, model pipeline, because now we are going to do very complex set of activities. We have a training data set that we have separated from our ABT. Now we want to build multiple models with lasso, with ridge, with elastic net, random forest regressor, gradient boosted tree, and again each of these algorithms have multiple hyperparameters, and we want to tune these algorithms as we train our data set. Using our data set, we train these models. We will use multiple values for multiple of these hyperparameters. That is one aspect. Another aspect is that we have to tune. For tuning, whatever training data we have, we want to use tenfold cross-validation mechanism. We want to run 10 multiple iterations by keeping a holdout fold every time, a separate holdout fold, and other 9 as training folds. And then while we do that, we want to average the cross-validated score for every one setting of the hyperparameter, and then run multiple of them for all the algorithms. So it appears a lot of very complicated affair, because as technical people, whenever we talk, first thing comes in our mind about how do I code this. Okay, so as we are thinking, it's a real complex problem. But then to solve this complexity, there is this approach called pipelines. Basically, pipelines are a mechanism to automate these complex workflows using some existing classes, functions that are available in our scikit-learn algorithm. So we will look at them, and as we progress, you will see how easy and how formulaic this whole process is. But you have to remember this formula. You have to understand why we are applying the formula in whichever way we are applying, underlying whatever under the hood, what is happening, try to understand. But then once you understood it, in every project that you undertake in the future, you can use the same time tested kind of method to build these models and select winners, all that. So carefully follow, and I encourage everyone to take your time, and whatever code we do, I will go slow only for the first project, but next project onwards, same process we will do, so we'll go very fast. But for this project, I want to go slow. I want to ensure that you people are doing along with me. So the second step is model pipelines. Today we'll do that. Then anyway, the third is hyperparameters. So we'll club all of them, the pipelines of scaled or pre-processed model pipelines. We will combine with hyperparameters that we declare, and then everything we will fit inside a loop of cross validation and build multiple models and finally select winner. Okay, so yesterday we did split data set. We are ready with that. Now today we will go with this second step of our model training process, that is build model pipelines. Okay, again, don't worry this pipelines and that word. Basically, a pipeline is a way to automate a complex workflow. We use this kind of pipeline terminology when we also talk about continuous integration, continuous delivery. So the pipeline is something moves swiftly through the pipeline in an automated manner, however complex that is. Okay, keep that in mind. Are you with me?
Yes, sir. But staying with split data set, I have a thought, sir.
Okay.
So
Go on, please.
can we use the abstract data set as our training data set?
What is abstract data set?
Sir, ABT, analytical base table. ABT, sorry.
Okay. Yeah.
Can we use ABT as our training data and split the raw data for the test data?
No, but raw data, the shape of the raw data right now has, because raw data and ABT are same. Only thing, raw data has been cleaned and feature engineered to arrive at ABT. It is a transformation that we did on the raw data, and we came up to ABT, which has raw data. We started with some 25 features. ABT has become 40 features, and some rows we have removed over the process of data cleaning. Okay, but why are you kind of bent on using that? What is the benefit you think you are getting by doing that?
Right, sir. Yes, sir. Because the unseen data will resemble the raw data.
No, but unseen, whatever ABT is transformed from your raw data only. It is not unseen data. It is the same data that came. Only because we cannot use that directly to train a model, we did all the pre-processing steps. Now, if you want to really test with unseen data, it has to be from the field of the customer. Maybe customer is getting some queries from some of their customers and asking, hey, this is the property, details of this property. Can you tell me what price can it go? Then customer should be able to build an application using the model that will give it to them. Then the customer data entry operator will fill the new data and submits. Then it will tell the potential prediction for the transaction price is 200,000. Now, if 200,000 is better than an inexperienced appraiser's output manually using his or her brain, then it's okay. But actually, anyway, coming back to your question, I don't understand why, what benefit will you get by using raw data set to test? I don't understand that.
Right, sir. 2 points there. One is the unseen data will resemble the raw data that we have because it will be in the same format. It will not be in the modeled format. The unseen data will not be in the modeled format and will be exactly in the that is one. Second is while we are doing a split, we are removing 20% or some ratio we are removing. So maybe we are tinkering with the model with this analytical based data.
No,
So
okay,
these are the
whatever.
2 points.
Yeah, but whatever you do, you okay, what I'm hearing from you is that you are telling that you have less data to train because you have removed 20%. That is the issue you are telling. Okay,
Right,
am
sir.
I right?
That is second point. Yes, sir.
Yeah, but the second point you are talking about is raw data will come like raw data. That is true only. Okay, raw data will come like raw data. So let me, where is this? How do I new?
Madhu, adding to that one, I have also a question.
Just 1 minute, 1 minute. I am figuring out this. Okay. Okay. Go on, Amir.
Yeah, the test size we declare, right? Is it standard across the industry, the 20%, or it is up to us to declare whatever it is?
It is up to you to declare, but usually if we make test as a bigger percentage, then you will have less data for training. So anyway, you have to decide it based on situation to situation. Let's say you have lot of data anyway, so 30% I can reserve for testing. Reserve it. No, nobody can stop it. It is just put that argument as 0.3 at the time. That's it. Nothing beyond that. Okay.
Okay.
Okay. So actually, I talked about this point. Mr. Ramshankar mentioned that actually we had a kind of data customer has given us. Okay. This we are calling it as raw data set. Okay. Okay. Which had total, including our target variable, some 26 features. Okay. 25 are input features and plus 1 is our target variable. Okay. This is input feature. This is our target variable 1. This is how data came to us. Okay. Now, on this, we applied a lot of steps to bring up to a data. Right now, we have a cleaned feature engineered data. Okay. And we are calling this as analytical base table. To arrive this place, we have done some mission critical code. I always copied. Okay, this is my data cleaning that has manipulated this data cleaning code. Okay, then after this I have made few more transformations using some code. This is feature engineered code. Okay, and after that I saved and became my ABT. Now by the time it became actually there were few observations, 1883 observations and 26 features, 25 input features and 1 target variable. But by the time I completed my transformations, okay, then my shape of my ABT has become 40 into 18, some it has some at least
1864. 64.
okay, whatever. So some observations have been removed as part of this data cleaning, and also as feature engineering we added extra columns from various purposes. We did that. Now on this actually I am putting my training set and testing set. Again, as Amir asked, it is up to you, 80 20 70 30 50 50, but it is up to you. But keep substantial amount of data for actually training, because more data only proper training can happen. Now what Ramshankar is telling, that why don't I use for my training set this if you have, let's say this is the data you got, but then next 2 months customer gave in the same shape means 25 into 26, and let us say customer gave 100 more records, okay, in the same shape. Okay, and now you will apply, like by this time, this is raw data. In fact, the customer will have always data in this only, because that is how they are collecting. But using this data, we built a model. Now using ABT, now we will finally build a model. Okay, winning model. That is what we are doing right now. So we supply it to customer. Then customer, what he will do, as customer is running his business, new raw data keeps arriving. So this anyway he will apply here and ask for prediction. Okay, when customer gives data in this shape, 26 into 100 now, or 100 observations new, so far they are come in the last few weeks only, and model is there. Instead of a person sitting here and deciding what is the transaction price for these 100 observations, now what is happening, the model is deciding what is the transaction price, and it is doing better than this person, let's say. That is how we created a model for them, our customer. Now customer cannot pass this data in this shape to the model. Customer has to apply this code and this code on this data and transform it. Then only it will get the shape of ABT, and then only he can pass it on to the model, and then only model will do the prediction. That is why I've been telling previously also, whenever you are doing some code that you are changing your data set, you always keep it aside as a mission critical code, because this code can be converted into a Python class and also supplied to our customer. Then customer can, whatever this input data is there, they can build an application where they use this code as well as this model to build their own software application to do this. Okay, but this is the only data customer gave at the time of model building. So I am manipulating that only. Now whatever new data, anyway we will do that. That is the brand new data. That is where actually the business is getting benefited because of the model. At the time the model is really being field tested. Okay, am I making sense?
Yes, sir. Getting it.
Okay, so whether you, this 1883 again became 1864, but using this, or if you want to use like this, then you have to run this programs on this and convert into the same shape, then only you can. Otherwise two data sets will be of two different shapes, numpy will not work. Okay, then nothing will work. So you have to always ensure that the shape of the data set is the same, otherwise it won't work. Okay, are you there?
Yes, sir. Got it, sir.
Okay, so we will do this model pipelines. As I told you, our data is almost good, but our data has still a problem. What is that problem? The problem of scaling. Each of the input features, because of their nature, they are representing some numbers of different scales. Then sometimes with some algorithms, actually that kind of different scalings can be problem. So algorithms may not kind of estimate some things properly. They may estimate little bit more for a larger numbers and small for a small number. So to make it easy for any algorithm, we transform this data. We try to use a statistical technique and put all of the features, input features, into a standard scale. Okay, so that's what we call scaling. So before we pass our ABT data to our algorithms, we have to take this action. Okay, and that action is called pre-processing or scaling your, or standardizing the data, or standardizing the input features. So we do that, and because we have to use it in a kind of cross-validation kind of cycle with multiple algorithms, with multiple settings, we have to use pre-processing of the data within a pipeline, in a workflow. We should not do manually from outside. It will not work. It will become very complex. So that's why we are going to build today something called pre-processing or model pipelines. Okay, so that is what the step we will do. Some coding also will be there. Get ready for that. So I'll quickly talk some theory first, and then we'll go to the coding. So our goal is to build a pre-processed model pipeline. Okay, so in steps 1, 2, and 3, we explored the data set, we cleaned it, and we engineered new features. Okay, most importantly, we created an excellent analytical base table that will set us up for success. So we have done significant amount of work in our steps 1 to 3, but we have to still talk about pre-processing. Okay, however, sometimes we will want to pre-process the training data even more before feeding it into our algorithms. This is what standardizing or scaling, or bringing all the features into the same scale. Okay, for example, we may want to transform or scale our features. Okay, there are many types of scalars, statistical methods, standard scalars, min max scalars, and all that. So we have to apply that statistical transformation onto our input features before we feed them into our algorithms. Again, there is another technique sometimes we have to apply, that is called perform automatic feature reduction. A technique is called PCA, that is called principal component analysis. In fact, we learn this. This is a very important algorithm to reduce your dimensionality. Okay, so whenever there are data sets with too many features, too many means really too many features, then we land up in a situation, and that we call is actually curse of dimensionality. So to automatically solve that curse of dimensionality, there is a statistical technique called PCA. This is also again a pre-processing thing. Before we pass on the data set to algorithm, we may have to run this. Actually, PCA is also considered a smart algorithm. Even StandardScaler is also a functional, a good algorithm type function only. Okay, so sometimes you try to remove correlated features using some transformation techniques. Okay, these are all called pre-processing steps. Based on whatever problem to problem, you may have to do this. Okay, sometimes you may have to apply min max kind of scalars or standard scalars and all that. So we'll not go into the theory of that, but just keep in your mind that pre-processing means you are transforming, applying some transformations on your data set before you are feeding them into your algorithms, because that will help to build a proper model. Otherwise, algorithms may get a little bit confused. So keep that in mind. So the key is that these type of pre-processing steps should be performed inside the cross-validation loop. We have to theoretically understand what is this and how it is done manually, but because now we are training models with multiple algorithms, these multiple algorithms are coming up with multiple hyperparameters, and these multiple hyperparameters we have to try multiple values, and in a cross validation loop we have to do all that. Then the pre-processing has to be also done inside cross validation, because we keep on changing. In 10 iterations we will do 9 into training folds, 1 as a holdout fold, then we change another 9, another 1 to hold out. That whole process is very complex. So Pre-processing always is done inside the loop of cross validation. Okay, so hope you are with me. Let me move on. So standardization is one technique. That is what we apply to our project now in a regression thing now. PCA will apply. Actually, you will learn about PCA in a decent way when we do our fourth project, that is our building cluster model, cluster analysis we'll build. Then we will look at unsupervised learning problem. Okay, for now we'll talk only about standardization. Standardization is the most popular pre-processing technique in machine learning. Okay, so what is that? Standardization, it transforms all of your features, now 40 features out of that 39 input features, okay, features, to the same scale by subtracting the means and dividing by standard deviation. So right now we have a lot of columns. Okay, let's say this is square feet. Okay, and let's say this is lot size and beds. These are the column. Like that I have another whatever 36 columns are there. Okay, now square feet has some values: 500, 1500, 2000, 1200, 1100, 950, 750, and lot size also we have 100,000, 50,000, 25,000, like that it is there. Beds also 2, 3, 1, 4, 6, 2, 3, like that it is there. So these are my input features. So what I am telling, standardization, by applying standardization, I want to transform each column. Column is nothing but a feature. What I will do, all of my features to the same scale by subtracting the means and dividing by standard deviation for each of the observation. Now let's say I am doing a square feet standardized, I want to calculate. So what I will do, I will take each observation. 500 is my first observation. Let's say for this column, mean is, let's say, 1700 and standard deviation is some 950. So what I'm going to do, 500 minus my mean 1700 divided by my standard deviation 950, whatever is that value I put here. Then I go to the next one, next one, next one, and this square feet scaled square feet will look like this, new column. So every column I am going to change it. How I am going to change? I will calculate the mean of the column, I will calculate the standard deviation of the column, and for each observation in that column I will subtract mean and then divide it the value by my standard deviation, and that is what we are going to do as what we call standard scalars. When we apply, that is the technique, that is a transformation. We do that on every column. So what is the effect of that column? So this is useful pre-processing step, because some machine learning algorithms will overemphasize features that are on larger scales. That is why it's a very important step. So if you don't do this, a lot of times, a lot of people forget. They don't do it. They are very excited and they pass it on, ABT the way it is, and build models. But when you pre-process, the results will be much better. Okay, that is why this pre-processing is a very important step. Okay, so first you have to subtract its mean from each of its observation. That's what we did. 500 is my first observation. Mean of this column is 1700. Standard deviation is 950. So first subtract its mean from each of its observation. We did that. Then divide each of its observation by its standard deviation, and whatever that value is a scaled value. So what happens? This makes the features distribution centered around 0 with unit variation. Variance means your mean will become, after transformation, your mean will be 0, your standard deviation will be 1. Okay, so that is what we talked and we created noise in our toy project. We created such a noise. We talked about it is a normal distribution. So with mean of 0, standard deviation of 1, that is what really the transformation we are applying. Are you with me so far?
Yes, sir.
Yes, Guru.
Okay, so manual standardization, though we will not apply manual standardization because it has to be applied within a whatever a loop of cross validation, and we have to really use a standardization, whatever standardization we are doing, some good scalar program we have to use. So but let us show the summary statics from our training data. So what I want to do is that if yesterday's IPYNB file is there, run all of them. Okay, just go there and run all of the cells. Maybe let me go to my thing also. Where is my regression analysis model training? Okay. So yesterday we did up to here. Okay. Train test split. I'm first going and running my header where I'm importing my numpy as np, pandas as pd. Actually, if you have all the code till yesterday, what you can do is that you can go to kernel and restart and run all. Then it will run automatically without you having to press again and again. But I'm not doing because I have the appended code also. So okay. Then what we did, we imported all of our algorithms because these are the 5 algorithms we are going to use. Then I read my analytical base table, which has 1863 observations with 40 columns. Then what I did, I actually imported my train test split function from my model selection library and imported it. Then before I ran my train test split, what I did, I separated my input features and gave it capital X variable name, and the other whatever remaining Y target variable, I am calling it as small y. This is a very common notation. Input features are given capital X, target variable small y in a supervised learning kind of situation. So I did that. I separated my input features and target variable. So my then on that I'm applying my train test split, which will return a tuple of 4 elements, 4 smaller uh, data frames, x underscore train, x underscore test. Then target variable also is again split, y underscore train, y underscore test. I gave them variable names, so I remember it and keep it for my future use. Okay, so then yesterday we stopped here. After splitting, we just checked how are my because 20% split I did, so equally everything has been done. Okay, so that is where we stopped yesterday. So all of you come up to that step now. Have you come up to that step?
Yes, sir.
Okay. So let me go back to our this thing. So what we will do is that to understand what is this manual standardization all about, first do your, because now we have capital X underscore train data frame, which is a smaller data frame. You go and describe that statistics you see. First, let us show the summary statistics from our training data. Our training data is X, capital X underscore train, or whichever name you gave. You run this dot describe function on this and tell me when you are ready.
Yes, sir, ready.
Okay, so this is our split data with only train input features, capital X underscore train. So it has 1490 observations. Okay, for all columns, because now it's a ABT, so no nans and all. But actually, let us look at the mean. Okay, mean of beds is 3.434. Mean of baths is 2.579. Not a problem. Both of them are on the same, approximately same scale. But if you look at square feet, the mean of square feet is 2,322. Mean of lot size is 12,746. Okay, so shopping 39.561. So means are all over the place. Then you also look at the variance from the point of view of standard deviation. Beds, the standard deviation is 1.03, 073. Lot size 34,805. Okay, this can cause a problem if we, without pre-processing or without scaling all the features to same scale, if we pass this data, there can be some problems with a lot of algorithms. Some algorithms internally take care of that, but assume that algorithms don't take care, then we have to scale them. Okay, the means and standard deviations are all over the place. This can be a problem for some machine learning algorithms that assume features are all on approximately the same scale. That is the problem that we are solving. Okay, are you there with me?
Yes,
Okay,
sir.
can I move on? Yeah. So now manually, let us standardize our X underscore train. So what is really, I'm creating a new table data frame, and that is why I'm calling X, capital X underscore train underscore new. How I'm creating? I'm creating from the unscaled capital X underscore train, and we are calculating on that mean. When we calculate mean on a pandas data frame, the element wise maths happens, and mean for every column will be calculated, and that is subtracted for the respective columns. So this is so simple because NumPy uses the element wise maths, okay, to create a standardized scaled down or rescaled table. It is a very simple thing. This is the formula we are applying. For every observation of every feature, we are subtracting the mean of that feature or mean of that column and dividing by the standard deviation of that column. Okay, so do it and tell me when you are there. So basically, first we will subtract the mean. When we are doing this, all 39 columns of your X underscore train, this will be applied because NumPy underneath uses element wise maths. So that is the power actually. Then we are subtracting by the standard deviation and populating the new table X underscore train underscore new with the new scaled features, where the standard deviation will be 1 and mean will be 0. That is what the standard scalar formula. Can I move on?
Yes, sir.
Okay, now do a describe on this new scaled data frame, that is our capital X underscore train underscore new. On that, run dot describe. Okay, and actually before you do that, you may see lot of scientific kind of numbers, very precise numbers. Okay, so there is one PD set option which we have to apply. Let me, okay, so let me also do, I have done my describe. So we have seen standard deviation, mean all over the place. Then this is the standard scalar formula we are applying, and I am seeing my new thing. actually the problem here is that it is zeros will be very, very small numbers. So if we want to see, we have to suppress using some PD set dot set underscore option. So run this, okay, to suppress the scientific expression here, numbers. Run this once. Are you able to see that instruction? PD dot set underscore option, because yesterday in the header I have put it, but most probably you may not have typed it. Okay, because this is a little bit complex thing. Okay, typing. So what we are doing, PD dot set underscore option, argument I am putting first is actually string, that is display dot float underscore format. So float format I am creating a new option for me on that. So I'm applying some this lambda function, lambda x colon. Again, the format is string percentage 0.3f. Then we are putting percentage x. So type like that. Just this is how we can suppress some of that scientific notation of that numbers there. If we have done without problem, then again run this describe. Let me run this step now for me. So then I will run my describe again. Then I will see a better data. So if you tell me when you are ready, just type this the way I typed it here. Don't forget about those strings, wherever strings are there, quotes.
Yes,
Okay, so now if you describe again, we can see the numbers in a whatever after decimal 3, only that precision numbers you can see now more easily. So if you look at it, what happened? The means have become 0. The standard deviation has become 1. This is a normal distribution, normally distributed data. That's what we transformed our original ABT data with this, because they were falling all over the place. The scales are not all uniform. So we made it more uniform. Okay. Now, another important thing that we need to look at. Okay. So basically, the means are all now 0, centered around 0. The standard deviations are all now 1.0 with unit variance. Practically, this just means all the features are now on approximately the same scale. Okay. Now, this is actually transformed training set. Okay. Now, when I test, how do I apply these transformations? With what standard deviations and means I have to apply on my training features, not training features, test features, because we have actually already separated data. Some data is train and some percentage as test. Now, train is now scaled. Okay, using some means of each column and standard deviation for each column. Now, when I transform my test, because even before testing, I have to scale down that data frame also. Okay. Now, what means and standard deviations I have to apply? Should I calculate the standard deviation and means of those test columns, or should I use the already calculated parameters, these parameters? That is the question. So actually correct way is we have to use these parameters that are already calculated for your training set. You have to apply on your feature, like the test feature, there is a square feet column. Okay. Then there is a value. How do I transform this? This value, let us say it is a 1250. Okay. And the mean I calculated on train, that is, let's say 1500. and standard deviation I calculated say 900. So this value I will put it, not the mean and standard deviation calculated for this test column. Keep that in mind. Okay, that is what we want to show it here. Pre-processing parameters, these standard deviation and mean that are calculated on your training features, they are called pre-processing parameters. Okay, like right now we have talked about 3 parameters as we came so far. We talked about model parameters, those are betas that are learned by your algorithm when you train using a data set. Then we talked about hyperparameters. These are externally tunable values by the machine learning developer. And now we are talking about another set of parameters. These are pre-processing parameters. These are the standard deviation and mean calculations performed on your training data that you have to apply it in on before you testing. In fact, in the cross validation kind of time, actually every holdout fold has to be again scaled to, so in 10 iterations, every time you have to use, for the 9 iterations you have to calculate these parameters, then apply for the holdout fold those parameters. Then next iteration you calculate again for the new 9 training folds, and then apply the standard deviation and mean for the holdout fold, the changed holdout fold. Like that you have to keep on changing. Okay, keep that in mind. So now that the manual standardization we just performed is nice for seeing how it works, but it is not how we will do it in practice, because it's a very complex step. As mentioned earlier, we need to perform pre-processing steps inside the cross validation loop. Okay, here is why. To perform standardization, we need 2 pieces of information. What is the 2 pieces of information? The means of each feature and the standard deviation of each feature. Okay, from the training set. These are the 2 parameters, and these are called pre-processing parameters. These are called pre-processing parameters because they actually needed to be learned from the training data. Okay, so standardizing the test set, how it has to happen? There is a, so what if we want to pre-process new data such as our test set or holdout fold set? Okay, should we do it in the exact same way? We need to use the exact same pre-processing parameters that we learned from the training set. We should not calculate again them for the testing set or actually holdout feature set. Okay, not from the test set. Are you with me?
Yes, sir.
Okay. Mathematically speaking, this preserves the exact original transformation from training that we are applying on the testing, rather than calculating again, making test set on its own again, mean 0, standard deviation 1. We should not do that. Why we should not do also is that, practically speaking, if new observation comes in one at a time, like say we have built the model like whatever Ram Shankar told. Okay, now new observation came in the old way of 25, only one observation came. Okay, this is actually having 24 input features plus 1. Actually there is no target variable, that is what we want to predict. Okay, so only we have capital X values. Okay, now on this, using this model that we created, we want to run this and make the model to predict, not a human being to predict, but model to predict the transaction price. Okay, what we will do, because this is in the raw form, I will first run the code that I developed in the data cleaning and feature engineering. Then I have to also apply my pre-processing, okay, on this data. At that time, only one observation is there. What is the mean for this observation? What is the standard deviation? There will be no value. So that is the practical reason why we should not use the new data sets or testing data sets means and standard deviation to pre-process the testing data. To pre-process the test data, you have to use already calculated pre-processing parameters for the training set. Are you there with me? So practically speaking, if new observations come in one at a time, you can't standardize them without already having some pre-processing parameters to use. That is, those learned from your training set. Okay, that is why we have to be careful. A lot of people again make that mistake. So what mistake they do? You tell me. This is two ways. What mistake is there in this? Can you spot the difference in the next cell? So this is, I am actually scaling my capital X underscore test underscore new. Okay, here what I'm doing, the X underscore test features I'm taking, the values, observations, each observation in each column. Then I am subtracting with X underscore test dot mean. So I'm calculating for the testing features mean, subtracting and then dividing it by X underscore test dot std. This is wrong way. What is the right way? X underscore test minus X underscore train dot mean divided by capital X underscore train dot standard deviation. This is the right way. The first one, you are calculating mean from the new test features. Don't do that. Similarly, standard deviation. What is the right way? You have to apply your pre-processing parameters learned from the training set on your testing before you do the predictions. Okay, this is the right way. So anyway, put this code in your both lines on your IPYNB, because I want the second line to be run and we want to do a describe of your X underscore test underscore new dot describe and see what are the values now, how it scaled it. Tell me when you are ready. Are you there?
Yes, Madhu.
Okay. So the first one is wrong way. So second one is right way. So keep it in mind. So whatever pre-processing parameters that you learned from training set will be applied to scale your test features before you start making predictions. Okay, so this is the wrong way and this is the right way. Now you would subtract the training sets means from the test sets features. Keep that in mind. And then you divide the test sets features by the training sets standard deviation. Okay, that's what we did. That is why you actually need to save the pre-processing parameters from the training set. Okay, so anyway, this is the manually understanding things, but you will not do like that. You will use in a proper loop using a pipeline. That's what we'll talk right now. Okay, so let us take a look at your capital X underscore test underscore new. This is not train, it is test. So you have applied now your transformation on your test features, whatever you have split for testing, and look that describe. So and see the values here. Basically, if you look at the values, means are not 0, standard deviations are not 1, approximately there, but because you have not applied the testing features means and standard deviation. When done correctly, the features in your transformed capital X underscore test underscore new, this is our test features, are not guaranteed to have mean 0 and variance 1, although they will often be close. This is the right way of doing things. Okay, so just little bit of conceptual view of why the scaling is important. And here in this case we are using standard scaling. Okay, so in some other projects, some other situations, we will use different kind of transformations, like in our cluster analysis. At the time I will talk to you, and that's a much more complex theory, that is PCA, principal component analysis for dimensionality reduction. We'll look into that. Okay, so for now let us understand, so pipelines and cross validation. So now this is a very complex process. So if you look at, I have a trained data. Okay, then I have test data, and even training I'm using 10-fold cross validation. Okay, then I have multiple algorithms. Okay, and I have multiple hyperparameter settings. So many variables, and I have to do this now. Like for example, even if I take lasso algorithm, then I want to try with lambda 0.1, lambda 0.2, lambda 0.5, lambda 0.7, lambda 0.9. These are the 5 values of my lambda. I want to try lasso algorithm for my training, and then test and evaluate which particular one worked. We'll do it later, but even now, even in the training process, we have to train and tune. So what we will do, I will first take lasso algorithm. First I have my data first. Okay, the data I have to scale it. So calculate my pre-processing parameters. Okay, on my 9 folds of the data, then apply that on my holdout fold. Okay, then I have to call my lasso, and I will have to set it with 0.1. Then this is my iteration 1. Iteration 2, I will select new 9 folds. I calculate my pre-processing parameters. I apply it on a new holdout fold. Then I call my lasso, run it, and calculate my whatever score. Then I will go to I3, then another 9 folds, another new holdout fold, and calculate my parameters, pre-processing parameters here, and apply here, and then call my lasso with 0.1 and do that, whatever. Then I calculate and average my cross-validated score for the first one, 0.1, and it, let's say, 0.57. Then I will start again with lambda 0.2, same process again. I have to do that. I have to do the same process. So much iteration in loops we have to do that. Okay, so as you will recall, we will be tuning, that is finding the best setting for our model with cross validation. So this is a very complicated process. If you think that you will try to build a code yourself, okay, even thinking itself is so complex. Okay, so that is where actually these model pipelines come and rescue us from this complexity. So as I told you, pipeline is a process of automating a particular workflow. Okay, so let us see. We will split the training set in 10 different folds. In the tuning process I'm talking. Therefore, when we apply pre-processing, we should only learn pre-processing parameters from the 9 training folds. Okay, in each iteration. In other words, we need to store our pre-processing steps in a model pipeline and perform cross-validation on the entire pipeline. So that is the process we have to do. That is why we have to automate a workflow, thinking through something that moves step by step in a sequential way, one step after the another step, all that. That thinking process, we are calling it as pipeline. Again, our scikit-learn has a function or a class called make underscore pipeline, and you pass what kind of pipeline you want, it will create for you a new object, a pipeline object. You can use it at the time of your model building using a cross validation object that we'll talk later. So far, are you clear with me?
Yes, Madhu.
Yes, sir.
Okay, fine. So let us move on. So let us look at this process, 10-fold cross validation with pre-processing. Already we took pictorially, we looked at our 10-fold cross validation, how it works. So you have a mental model of that. Now combine that with pre-processing. What happens? Let us look at it. Here is how the new 10-fold cross validation process would work along with your pre-processing. So first we will split our data into 10 equal folds, pre-process 9 training folds, learning the pre-processing parameters, the standard deviation and mean for those 9 training folds in the first iteration. Train your model on those newly pre-processed 9 folds. Okay, so you will train using the scaled data for these 9 pre-processed folds. Now we have to validate with the holdout fold. So pre-process the holdout fold using the same pre-processing parameters from the training folds. So do that and then validate, get a score. Evaluate your model on the newly pre-processed holdout fold. Okay, then perform steps 2 to 5 10 times. Okay, you have to iterate 10 times by changing your holdout fold every iteration to another new one, and you average the performance across all 10 folds. Okay, that is what we typically do. 10k fold 10 fold cross validation with pre-processing looks like this. Okay, and this anyway we have to do for each value of hyperparameter that we want to create models and validate, and then for each algorithm. So that is the kind of complexity that we have to deal with. So how to make a pipeline? So you just learned a sophisticated modeling process that has been battle tested and proven in the field. This is how the real machine learning engineers in real machine learning development projects build models. Let it be machine learning or deep learning. Deep learning, the model may be the neural network, but the pipelines and all the concepts that we talked, regularization, ensembling, pre-processing, model pipelines, all the hyperparameter tuning, everything is even true for deep learning also, but the algorithms and the problems and the computational model only change. Okay, luckily you won't have to implement it from scratch. Okay, scikit-learn comes up with a very handy make underscore pipeline function that helps you glue all these steps together, because you are doing multiple steps. You are, when data comes, first you have to do pre-processing of 9 folds, then apply those pre-processing parameters on the 10th fold, the whatever holdout fold, then pass it on to an algorithm. That algorithm with that hyperparameter runs. All that is a very step-by-step sequential process. If we write code, we have to write, but you can abstract all those things using a ready-made function that is available in our scikit library. That's called make underscore pipeline function that helps you glue these steps together. So before we start using it, we have to import it. So go and import this. Where is it available? It is available in scikit-learn dot pipeline. You import make underscore pipeline. And when you are ready, please let me know. Are you there?
Yes. Done, Madhu.
Okay. Okay. So we have imported our make pipeline. Our life is very simple. So after importing the pipeline tool, we'll import the pre-processing technique. Now, lot of pre-processing techniques are there, but in this, we'll be using this for every observation and of every feature we want to mean of that column and minus it and then divide by standard deviation. That method, the technique is called standard scaler. So let us import that also. For standardization, standard scaler is exactly what we are looking for. So that is available in sklearn.preprocessing library. Many will be there. We are importing standard scaler, S capital, no space between standard and scalar. Again, scalar, S capital, scalar again, LER. Okay. Type this because this is the name of that class. So we have to type like that only. Otherwise, it will tell wrong. So we imported these two important classes to make our pipelines. Okay.
Yes, from StandardScaler import make underscore pipeline, right?
No, from sklearn.preprocessing
Oh, okay.
import standard scaler. These are all available in a sub library called preprocessing. Many will be there. Many tools will be there. Min, max, scaler, all those things. Got it?
Yes, Madhu.
Okay. So let us create a pipeline now, because now we have our pipeline. So using this make pipeline tool, we will create a pipeline that actually builds sequential steps of applying standard scaler first and then calling my model class. So we are passing two arguments here, make underscore pipeline, standard scaler. Just now we imported. So we want, whenever this pipeline is used inside a cross validation and we are building models, when data comes, the data will be first scaled according to standard scaler, and then whatever model I will call here, I will apply that data to this model. This can be lasso, this can be ridge, this can be elastic net, this can be random forest regressor, this can be gradient boosted tree regressor, any of those things. Okay, so let us do that. For example, to create a pipeline for lasso regression, we can use this function like this. So make underscore pipeline, and two arguments I am passing. First argument is my standard scaler class, okay, and comma, I am passing my lasso class with random state equal to 1, 2, 3 argument, because there is a lot of random things happen. All of us want same results, replicable results, so we have used this. Okay, so what it does really, this builds a more complex object, a pipeline object. Okay, these pipeline objects can be used now in cross validation objects, and we can do a lot of model fitting the models and all we'll do. So we'll do all that. So now we are creating a pre-processing pipelines for each of our algorithms. Okay, so it returns an object. Once you do this, it returns an object with type sklearn.pipeline.pipeline. Second pipeline caps, but this is the object type. Okay, so if you look at here, it is telling what steps will be conducted by this pipeline sequentially. First, it will apply standard scaler with whatever things that we have not given any arguments. Okay, default arguments it has taken. Then it will apply the lasso regression after that. Okay, if you go, you will see that also lasso things. Okay, so did you get this?
Yes, sir.
Okay, so
in addition to that, I got memory equal to none, Madhu.
What is that?
Memory equal to none.
Okay, don't worry now. We will see that, but if without errors it has done it, means those are all defaults that has taken. Okay,
Okay. Okay.
fine. Yeah. So this pipeline will standardize the data first, then apply the lasso algorithm. That is the pipeline, sequential steps that it has to follow. So this object is very important for our factory way of building models, lot of models at a time. That is what I told, formulaic process will apply. So in our formula, pipeline is a very important object. Okay, anyway, now we have as an experiment, we have done only for lasso. But we, in our project, we want to build 5 models based on 5 algorithms. So we can create one dictionary. Okay, anyway, with random state 1, 2, 3 for lasso algorithm, replicable result. So let us create for all 5 a dictionary. Okay, maybe start a dictionary with all 5 you can do at a time, but I want you to little bit exercise on our dictionary functionality, whatever you learned earlier. So first let us create a dictionary with 3 keys. Lasso, you call these things, these are your words you are giving. So small LASSO, quotes, small ridge, small enet. Okay, these are our keys. The corresponding value should be pipelines. So pipeline will be, your value will be make underscore pipeline in the brackets standard scalar, comma. If it is lasso, lasso with random state 1, 2, 3. If it is random forest, your dictionary thing will be RF, your key value. Then your value key is actually RF in quotes. Value is your make underscore pipeline. Then standard scalar is first argument. Second argument is random forest regressor with random state 1, 2, 3, 4. Something like that. We have to do that. So create a dictionary with for first these 3. Then we'll add for the trees also. You can put all 5 in single stroke. I'm just I want to check whether you are still remembering how to add new items to your dictionary or not. That is why I'm putting it. So what I'm doing here, I'm creating a dictionary of my pipelines, because this dictionary is going to be important. I will use this dictionary object in my factory model of creating models. Okay, that's why I'm creating this dictionary. Okay, so how I'm creating pipelines, I'm giving the name. You also give the name, any name you can give. But you remember how dictionaries are created with curly braces, and then you go to the next line with a tab space, key colon value. Key, actually I'm giving my own name, lasso. If you are giving like this, keep the spellings correctly like this only, because in the next step we will create a dictionary like this for hyperparameters. So we want to use the keys of these 2 dictionaries should be same. Then our factory will work cleanly. So that is why, remember how you are giving these names of the key names of your dictionary. Here I am giving it as small LASSO, small RIDGE, small ENET, and again I will give small RF, small GB. But how I am creating? I am creating the values using make underscore pipeline, standard scalar, comma, lasso, for lasso with random state equal to 1, 2, 3. Then ridge, again make underscore pipeline, standard scalar, but I'm giving a new class, regression class, ridge class, and with random state 1, 2, 3. And for enet, my value is make underscore pipeline. Again, standard scalar is the first step I will apply, and then my elastic net. So the name has to be like this. Have you done this?
Yes, sir.
Okay. Now, anyway, we want to apply 5 algorithms. Okay. Let us add random forest regressor and gradient boosting regressor to your pipeline dictionary. Already pipeline dictionary is there. How will you do it? Pipelines, in whatever index operator, the square brackets, and new whatever RF, your quotes, equal to, actually you have to give the value. That is again make underscore pipeline, standard scalar and random forest regressor. Like that, we will add those things. Just to, again, here itself you can do that, but I want to check whether still you remember your dictionary. Can you add new items to your dictionary or not? So do this also. So I am calling here for random forest small rf, my key name. Okay, then my gradient boosted trees, I'm calling it as GB, small GB. So you also use that, because in the next class I will set up a similar dictionary for hyperparameter tuning. Okay, we will use both of these dictionaries and pass it on to a cross validation object, a class, another complex program. Then whatever we thought the iterative way, things will work in a factory. Have you added this? So carefully type it. So are you there?
Yes, sir.
Okay. So we have created a dictionary of pipelines with all of our algorithms that we want to try on our project, 5 algorithms. So the dictionary is ready. Okay, just you can run this for loop, again checking your coding skills only. Let's make sure our dictionary has pipelines for each of our algorithm. So for whatever key values, you do this for key comma value in pipelines dot items. So you will get all these algorithm small names that you are given, those are printed. And also I want you to print type of the value. In fact, I removed that, but actually it will give the pipeline class, the type of the value, your make underscore pipeline standard scalar comma algorithm class. That is actually, because you are using make pipeline to create a pipeline, the object will be a more complex object, and that is your class belongs to sklearn.pipeline.caps PIPLINE. Okay, that's what we will get it. Now that we have our pipelines, we are ready to move on to declaring hyperparameters to tune. That is our next step. So up till here, now we created a pre-processing pipeline. We are not going to do that manually. Today we spent time to understand the concept behind pre-processing and how it will be done using a standard scaler, but we don't need to do anything. We have to only define a proper pipeline with the algorithm class and the type of scaling I want to apply on my data. And now I created a dictionary of my pipeline with various algorithms. Are you there? So let me go to my code once. Okay, and run up to whatever we have done here. Okay, so I ran up to here, then the wrong way and right way, and we have describing again. So the right way is basically you have to apply the learned pre-processing parameters from your training to do this. Okay, something happened here anyway. Okay, so we have to do that. Then we are describing it. Then what happens? So basically, because I ran that lambda function there to suppress the scientific thing, then we are seeing, so standard deviations are not 0, 1 here. Okay, they're close to 1. Similarly, means are all not 0. They're lower values. That is the right way. Okay. Then once we understood what is this pre-processing parameters, what is the right way. So we are building for our project now a pipeline, a pre-processing pipeline we are building. So how do I build? I have to use this tool called make_pipeline. So I imported it from sklearn.pipeline. Okay. Then I want to use StandardScaler for this project. So I'm importing my StandardScaler again. I am doing importing from sklearn.preprocessing. StandardScaler I imported. So both of those classes are there. Now for example, I'm creating a pipeline that receives data, uses StandardScaler as the pre-processing technique, and runs a lasso algorithm. So a pipeline, sample pipeline I created. So a new object has been created now. This is a pipeline object, okay, which actually is putting sequential steps. I will apply first StandardScaler with these arguments, then with lasso I will run on that standardized data. Okay, like that it has put it. Okay. Then what we did, we are playing again with this. I'm doing only for lasso and ridge. Then I added enet, but you can put all of them together. Okay. Then again, if you want to print these things, so here in the second one, ridge, it applies first StandardScaler steps on that ridge algorithm. It applies. That is my pipeline, second pipeline. Like that, I added all pipelines, 5 pipelines into a dictionary now. Okay, one single dictionary, and we created our 5 pipelines that we will use at the time of training our algorithm. But still, one step is left to start training, and that is actually for each of these algorithms, I have to review carefully all my hyperparameters and figure out a way to integrate that into a dictionary. And these 2 dictionaries, if I pass it on to another cross-validation object, using that I can fit my models and train. Okay, so we have done this. Then type of any of these, what is that? Types are pipeline objects. Okay, sklearn.pipeline.pipeline. Okay, these are new objects, pipeline objects. Okay, then anyway, whether I set it up everything correctly or not, I'm seeing here. So all lasso spelling mistakes are not there. Everything is there, and everything is a pipeline type object. So this is what we did today. Okay, so let me know if you have any questions. Okay, any questions? Did you understand everything clear? What we are doing and why we are doing?
Yes, sir. Clear.
Don't have any. Yeah. So if you don't have any further questions, so let us close here and see you tomorrow then. Bye bye everyone. Learn, have fun.
Thank you, sir. Bye.